Oh. Okay. All right, so a quick in the news. This one's a little bit of a stretch maybe, but it's interesting. The UN decided that today is the day that world population crosses the 7 billion mark. And in the past, when we crossed 6 billion, they actually picked a random baby and said that that was the 6 billionth baby. They decided not to do it this time. But the reason why I think this is 61C in the news is because a lot of the decisions that we're going to be making, or you're going to be making when you're thinking about designing, computer systems, or big infrastructures or whatever, you're going to have to do back-of-the-envelope calculations about, how to scale your system, how to size your system. So, for example, you might think, well, I'm creating a new social network, and what percentage of the world's population, could I, in my wildest dreams, get to sign up? And maybe you'd say 10%. Okay, well, if you said 10%, you'd have about 700 million subscribers, and guess what? That's about what Facebook has, right? So, on one hand, so you need to be able to do that kind of calculation, so you have to have these kinds of numbers kind of at your fingertips. So it's good to know there's about 7 billion people in the world. Now, not all of those people today have computers, so they're not all part of your addressable market. But, you just have to have that sort of understanding of scale. And then the other thing is if you're wondering if, your favorite social network is kind of starting to top out at its, its maximum ability to get subscribers, you realize there's actually still quite a bit of headroom, even the biggest systems. So, I put this up there just so you start thinking a little bit about this type of back-of-the-envelope calculations, because it's important to be able to do. So 7 billion people, and it's the UN is projecting that growth is eventually going to slow down, and it's not going to double for another 70 years or something like that. So, kind of an interesting thing. All right. Welcome to the Halloween lecture of 61C. I'm glad to see at least a couple costumes out there. Let's hear it for people with Santa. Anyone else? Yeah, good. My daughter tried really hard to get me to wear a costume, and I wimped out. I'm sorry. All right, and Dan, Dan's kind of got it. He's got it. All right, so we could expect that. All right, good. So, all right, so let's jump into it. So we talked about last time, we went through the 5 stages of the data path. Basically, you got to get the instruction, you decode it, and you read the registers. You do whatever you need to do in terms of arithmetic and logical processing. You access memory if you need to, and then you write the registers you write a register if you need to. Okay, and so remember, we do typically everyone does 1 and 2. Usually 3 happens, and then 4 or 5, happens or not, depending on what kind of instruction it is. All right, and then we talked a little bit about at the end about the timing of the data path, and we're looking at what's called a single cycle CPU, which is all 5 of these steps happen within 1 tick of the clock. Okay? We talked briefly about an alternative way to do it, where you try to break the clock into, you try to break these stages into individual clock ticks, and you make the clock tick faster. We'll talk about that again in a couple lectures, but for now, our world is, clock goes up, we do these 5 things, and we've got to make sure we get them done by the next time the clock goes up. Okay? All right. So what did that look like? Sorry, let me just get through this. This is just the picture we showed, and at the end of it, with our low-tech clicker question, we looked at this picture and said, it was actually a slightly more complicated version of this picture. It said, all right, there are certain places where multiplexers have to be put in because we're choosing between multiple inputs, and we only want to send one of those out at a time. We're going to see that again today. But this was the basic picture we had. And what we now need to do is, these are our moving parts, and they're not moving, hopefully, but these are all the parts of the system. And what we need to start talking about is a little bit more about how these things are put together, and then how do we control them, okay? And so as you probably know, the way we're going to control them is we're going to look at the instruction. And as you know, in MIPS, the combination of opcode and function code are going to tell us what instruction we're running. And that combination of opcode and function is going to drive a whole bunch of signals that go back from this controller logic back to control the different muxes and ALUs and other things that we have to control to make the bits flow the way they need to flow. Okay? So what we're going to start talking about now is this next part of the process where we're going to take that instruction and we're going to use that to drive the control of this data path. All right? And we'll get through a part of this today. We'll finish it up on Wednesday is the plan. All right. So we've got 5 steps in processor design. And these are not the same as the 5 steps of the instruction cycle. But basically, the first thing we're going to do is we're going to look at our instructions set, right? Because that's the interface. That's the thing that defines what our processor does. Okay, and we're going to look at the instruction set, and we're going to figure out what do we need to do? How do we build the data path to implement the requirements, right? To satisfy those requirements. And that means we have to understand what each instruction means, and we're going to look at a simple way of doing that called register transfer language. We have to have storage where it needs to be, and we have to be able to make sure things are wired together to make sure that these register transfers all happen the way they need to happen, right? So the first step is understand your instruction set. Second step is figure out what pieces you need to put together to be able to implement those instructions, okay? And think about how you're going to clock this thing, how you're going to get it to work, in timing-wise. Then we're going to put those components together. And today we're going to talk about these 3 steps. And on Wednesday we'll talk about the next couple steps, which is, really trying to understand how do we get the control signals to happen in the right time in the right place to get the operations we need to happen, right? So that's figure out the control and then basically put the logic together to make that control happen, okay? So the first 3 steps are all about understanding the requirements and putting together the building blocks and assembling them the right way. And then the last 2 steps are all about how do we actually make the control happen, okay? And we're going to blur the line a little bit for these steps, but just this is a good way to keep in mind, how to think about the problem and also how, how far we are along in getting the solution figured out. Okay, so quick refresher for me as much as for you guys. MIPS instructions have these different formats, and based on the format, I'm going to stand where you guys are so I can see it. Based on the format, the bits of the instruction mean different things, right? So we have 32 bits, and we have these R-type instructions where we have an opcode, we have 3 registers, information about shift amount if we need it, and then for some opcodes, right, we only have 6 bits. That doesn't let us describe a lot of operations. So for some opcodes, these function bits, these extra 6 bits are going to tell us more about what function, right? So for example, an opcode of 0 tells us we're going to be doing something with the ALU, and then certain function bits say we're doing an add or we're doing a subtraction or so on, okay? So we're going to, if we see an R-type instruction, we're going to parse it up this way. Immediate instructions only have 2 registers, and then they have these 16 bits of immediate stuff. And then we have even another type of instruction, jumps, where we have the opcode and the target address. And remember, for all 3 of these, the opcode is going to be 6 bits. So we can always look at the first 6 bits, and that's going to tell us not only what opcode we have, but based on the opcode, what the rest of the instruction is going to look like. So at some point, we're really going to take those bits and pull them apart and use them to drive the execution of the processor. Okay, now in this couple of lectures and in the book, we don't look at the whole MIPS language. We're going to look at a pretty small subset of it. And so the things we're going to look at are add and subtract, unsigned, or immediate, load and store, and branch. Okay, and obviously, add and subtract are R-type instructions, and then these three are all I-type instructions. Okay, so we're going to have to pull those apart differently. I think one thing, well, we'll get into it, but one thing just to keep in mind, in the R instructions, we're going to take R and RS and RT as input, and we're going to write the output to RD, right? That's how this, so, we're going to add RS and RT and put the result of that in RD. Okay, so that's how we're going to interpret those. In the immediate ones, we only have 2 registers, and so typically we're going to use RS as the source register, and then RT for those instructions is actually going to be where we write the result if we need to write a register. Okay, so it's just a little unfortunate naming convention, but you just have to keep track of that. Okay, so for R instructions, the result goes into RT. For I instructions, the result, I'm sorry, yeah. I'm sorry, for R instructions, the result goes into RD, the destination. For I instructions, it goes to RT. Okay, so just keep track of that. Okay, so very briefly, and we're going to revisit this again later, step 1 of the process is to understand the requirements of your instruction set. And there are languages to help you do that that are called register transfer languages. And a register transfer language basically is a way of encoding what the instructions do by focusing on the movement of data to and from registers. Okay? So we start off by reading the instruction that's at the program counter location. Okay, and that's either going to be, in this case, we're showing that if it's an R-type instruction, then it has these 6 fields. If it's an I-type instruction, then it has these 4 fields. Okay, but in either case, the first thing we're going to do is we're going to get the instruction that's at the memory location referenced by the program counter. Okay, so that's what that notation means. And then the rest of this notation is basically saying, okay, for each of the operations in our minimal subset of MIPS, what happens in terms of registers. So for example, here, if for an add, we're going to take the value of register RT, the value that's in register RS, we're going to add them together, and we're going to put that into RD, right? Whichever register is named in the RD portion of the instruction. Okay? Sub is the same way. For OR immediate, we're going to take what's in register RS. We're going to logically OR it with a 0 extended version of the 16 bits in the intermediate part. Okay, so remember, we're going to take the lower order 16 bits, okay? But in order to do an operation, right, our ALU is a 32-bit ALU, so we have to turn that 16 bits into a 32-bit quantity. So 0 extend means we're going to put zeros in the upper 16 bits of that thing. Okay, so we're going to 0 extend the immediate value, and then we're going to logically OR that with RS, and then we're going to put that result in RT. Okay, so this language is just specifying exactly what we want those instructions to do. And by the way, all of them also have the side effect of incrementing the PC by 4. Okay, so that's what this is showing. So do this operation and increment the PC by 4, right? Because you want the PC to point at the next operation. Anything else here that's worth talking about? I guess load and store. There's a couple interesting things here. First of all, they also have to extend the immediate value from 16 bits to 32. But there, that extension can't just be by adding zeros. It has to be a sign extension, right? Because it might be a negative value. So you want to make sure that when you extend it to 32 bits, you preserve the value, okay, whether it's positive or negative. The other thing to notice is what we're going to do is we're going to sign extend the immediate part. We're going to add that to the value, the base value that would be in register RS, and then we're going to go to memory and say, hey, give me whatever's at that address, and load it into register RT. Okay, and for store, it's the same kind of thing, except we're going to write what's currently in register RT into the location that we calculate by doing this addition. Okay, So the other thing to notice is that load and store, as we talked about last time, are doing arithmetic, right? Because if you have base and offset addressing, you have to add those together. And then finally, here's a branch instruction. And the RTL for that just says if the value at RS is equal to the value at RT, then you want to go to, then you want to set the PC to PC plus 4 plus the sign extended version of the immediate value, okay? Because that's the definition of branch in MIPS. It's the offset is relative to the next instruction. That's why we increment it by 4. And we saw that in the diagrams we did last time. Otherwise, if it's not, then just do what you would normally do. Just go to the next instruction, so PC equals 4. So the entire operation of this computer can be described just by talking about what happens to the registers for each operation. Yeah? I'm sorry, what was that? Yeah. Oh, thank you. So, okay, so we're counting, okay, sorry. So thank you for asking and for answering. Right, so this is here because we're counting by instructions, not by bytes. So we're basically, we should be shifting it, right? Yeah, that's concatenation. So we're kind of shifting it over by 2 bits so that we actually get the word, because when you write the branch, you're talking about instructions, not about bytes. So we have to multiply it times 4. Thank you. Okay, any other questions about that? All right. So RTL, by the way, you can imagine it's going to be more complex for the full processor because we have a lot more instructions than this. Also, you got to remember, MIPS is a pretty simple processor. We looked a little bit of x86 code, for example, and that instruction set is much more complicated. And so the language you're going to use to describe those operations is going to be, there's going to be more of it. Okay? And you might have heard, there are different RTLs out there. One that's sort of very popular these days is something called Verilog. And there are other languages out there. But the important thing is, if you use a standard RTL like Verilog, then there's a bunch of tools that you get that you can then apply. So, for example, there are tools to simulate the circuit, just like you get in Logisim. There are tools to actually test that it's correct. There are tools to actually take the RTL description and generate the actual circuit from that. So there's a lot of tools you can get, but it ends up being very much like a programming exercise. You need to debug this stuff. Just like when you write a program, it might not do exactly what you want the first time you write it. You have to go and debug your RTL to make sure that your processor is actually defined correctly. But the idea is that this language is at a much higher level than the gates and the signals that we're going to be talking about. Okay, so that's RTL. Okay, so step 1 then is we got to understand what our instruction set means. We're going to do that by coding up RTL, and that's going to be a full specification of our instruction set. And then, there's a bunch of things that come out of that in terms of requirements. So we need memory. And an interesting thing about memory is we're going to actually have 2 ports into the memory, one for instructions, one for data. Not surprisingly, we have an I cache and a data cache. Okay. For registers, we're going to need, if you look at the RTL, we're going to need 32 of those. We're going to have to read register S and register T, and we're going to have to be able to write register RT or register RD. We need a program counter. We need to be able to extend, as you saw in that language, either by adding zeros or doing a sign extension. You need to be able to do addition, subtraction, logical operations. In our case, OR, because that's the only logical operation we have in this subset. You need to be able to add 4. You need you need to be able to add 4 to the PC, and you need to be able to compare registers, right? Because if you look at that RTL, we have to be able to do this comparison. So basically, that set of requirements that we just talked about is what you get when you look at this thing and see all the pieces that are needed. Okay? So that's what we're going to do in part 1. Once we understand the requirements, then we say, okay, let's start looking in our toolbox in our part inventory, and let's start picking out the pieces that we need. So, here are some pieces that we're going to need. This is an adder. Okay, it takes two 32-bit quantities, and it outputs the sum of them. Okay, so it's a specialized ALU. It only does additions, and it does subtractions as well, because we have the carry in. Multiplexer, so we've got two 32-bit quantities coming in. We have selection line, right? Either 0 or 1. And one of those 32-bit quantities will come out the other side. That's our multiplexer. And then we have the ALU, which takes two 32-bit quantities, takes an operator line that tells you what operation you're doing, and then outputs a 32-bit result. Okay, so those are our basic building blocks. All right, so what does that ALU have to be able to do? Well, in our MIPS Lite language, it's got to do addition, subtraction, and OR. Okay, and it's got to be able to do equality for the branch on equal. And branch on equal, we're going to use a little trick. So if you look in the book, they have a more careful picture of the ALU. And one of the things that comes out of the ALU is a line called the 0 line, which basically is a little weird. It's set to 1 if the result is 0, and it's set to 0 otherwise. It's a little counterintuitive. And we use that to be able to do that equality check. How do you use the 0 output of the ALU to do an equality check? Yeah, subtraction, right? You subtract one from the other, and if the answer is 0, that means they were equal. Okay? So we're going to be able to just use subtraction to do equality checking. That's kind of cool. All right, and then if you look in the book, they have a more sophisticated subset of the language. So they do AND, they do the STL that we talked about last time, they do a jump, but we're not going to go that far. We might look at jumps if we have time. But this is our basic ALU. So it's much less rich than the one that we'd build for the full MIPS subset. Okay, and again, we know this is all we need because in step 1, we looked at our register transfer language, and these were the only operations, the only ALU operations we found. Okay. All right, so now let's talk a little bit about what these pieces are. So we need some memory, okay, and what's memory going to look like? Well, we have to have a way of passing an address into the memory, okay, because we need to tell the memory what address, what area, what location we're dealing with, okay. When we read memory, we got to be able to read 32 bits out of it, so we have a 32-bit data out coming from memory. When we write memory, we have to be able to pass 32 bits in, so we've got to have the data in going into memory. And then there's two other things that you'll see here. One is a control line called the write enable. So that control line, when the write enable is set to 1, that means the following, that when the clock goes up, when the clock raises, whatever is in that data in on those data in lines, if write enable is set to 1, will be placed by the memory into the address that's described by the address bits. Okay? So if write enable is set to 0, it doesn't matter what's on these data in lines, right? Nothing's going to happen. It's not going to update memory. As soon as write enable goes to 1, right, that's a control signal. What that tells it is that as soon as this clock raises, we're going to write the data in bits into memory. Okay? And so you can start to see how this idea of control starts to play in. Some part of the system is going to have to make sure that the write enable bit is set at the correct time. Okay? If it's not set, the write's not going to happen. So if you're doing a store, that store operation is going to have to set write enable, and we'll talk about how that happens. Yeah? Yep. Yeah, the write enable basically says, yeah, that when that clock goes up, that's when the write happens. Well, the control we're talking about is binary. Okay, so control bits are going to be either 0 or 1, but it has to be on at the right time. So there is a timing element to it. Okay, so it has to be, the write enable has to be on, you know, at the time that clock is going to go up. Otherwise, the write won't happen, or it'll happen later, and that's not what you want. Okay, so that's where the timing comes in. And are you okay with it? Yeah, so it's called a synchronous write. And I'm going to defer to Dan for all timing-related questions, by the way. Because that's the trickiest part of this stuff is the timing, absolutely. All right, any questions about that? Because that's sort of the first place where we've seen control really having a major effect on things. I mean, we've seen the MUX, you know, the MUX choice, the data choice thing, but this is really a big one, okay? And the important thing here is that clock is really only going to matter for writes, okay? Okay, this one's actually easier. We need a way to store a 32-bit quantity, okay, like the PC, right? So the program counter, we got to keep that somewhere. What's that going to look like? Well, you know, that's going to be this thing. It's going to look like a register, and it is a register. And so if you remember the D flip-flop that we studied, it looks like that, except it's also got a write enable bit. So basically, you know, the 32 bits come in. It says n bits, but we're going to do a 32-bit register. So 32 bits come in. When the write enable is 1, when the clock when the clock raises, whatever's on these data in bits gets put in the register. If write enable is set to 0, the register doesn't change, and it's basically always, you know, whatever's in this data outlines, whatever's in the register gets put out onto the data outlines. Okay? And of course, there's a bit of a delay from the time you do the write to the time that the data goes out. Yeah. Right. So why do we need this write enable signal? And the answer is exactly what you said, which is the data in may not always be valid. Okay, so we want to be able to just have whatever stuff is kind of flowing through the system flow, and we want to use the control to make sure that operations happen at the right time. So if there's, you know, we don't really care what's on data in until that write enable bit gets set. Okay, so that's going to give us a lot of flexibility in terms of timing and not having to worry about being super careful about what's on, you know, each line until, you know, we're the ones, you know, that's what control is about, right? We're controlling it. When we set write enable, that means, hey, what's on that bus is the right thing. Yeah.
So supposing this was a one-bit register, could you just implement it as a normal VTech flip-flop, but instead of passing in the clock, you pass in the write enable and clock?
If this was a one-bit register, could you? No, I think you want the write enable and the clock separate. Excuse me. Because they're serving two different functions. Really, write enable is basically telling you when what's on this data in line or set of lines, right? And the clock is making sure timing works and telling you, okay, boom, now update it. Yeah.
What I meant by and was logical.
Oh, logical and? So you could have, well, yeah, you could certainly have write enable and clock logically ended, and that's probably what's going on inside that thing anyway. I mean, I didn't tell you what's going on inside. I didn't drill into that box to see what exactly the gates are. Yeah. So you'd have to AND those together at some point. Okay. All right, this one's a little more interesting because we've been talking about registers all this time, right, since the very first class. And what are they? Well, now we can finally see what they are. So there's this thing called the register file. And the register file is going to contain, for the MIPS architecture, 32 32-bit registers. So we just looked and saw what a register looks like. Now we're going to build a bunch of those, and we're going to put them into a register file. Okay? So now, what we've got to be able to do is we want to be able to read and write registers but somehow we have to select which registers we're reading and writing. Okay? So what's happening here is we've got 32 registers, and then we've got these 3 input lines, register A, register B, and register W. Okay? And the convention is going to be that register A and B are going to be outputs of this thing. So when you put a register number on line register A, right, and each of these is 5 bits, because we're choosing one of 32 registers. Okay, so we need 32 bits to say which register we're interested in. Whatever register whatever register is identified on lines RA is going to get put onto bus A. Okay, so we're going to read those 32 bits from that register and put them on bus A and send them to wherever they're going. Likewise, whatever register is identified by RB, those 32 bits are going to get put onto bus B. Okay, and then in terms of writes, we have RW, which is going to identify a register to be written. Okay, again, 32 bits. And likewise, we've got a write enable and a clock, just like we had last time. Okay, so what's going to happen is, if you're doing a write, RW is going to identify which register is being written. Bus W is the input, so there's going to be 32 bits of input that are going to get put into that register when, just like we saw before, write enable is set to 1 and the clock raises. Okay? So it's like what we saw before, except now we've got 32 registers. We get to pick 2 of them as output, and we get to pick one of them that can be updated. Okay? What kind of instruction might that configuration be useful for? What's it sound like that we've seen already? Right, that's an R instruction, right? We've got 2 registers that we're reading. We're going to do some operation to them, and then we're going to write the result into another register. Okay, so this register file is going to let us do that. Okay, so now we're starting to see how those instructions start turning into, these circuits that we've been talking about. All right, any questions about the register file? So really what we're doing is we're just building up pieces here. All right. So those are the pieces we need. We need registers, we need register file, we need an ALU, we need some multiplexers and so on. So now we can start going into the third step, which is, okay, given those components, how do we actually start wiring them up so that they can do the operations that we described in our RTL, okay, in our description of the instruction set. So, what are we going to need? Well, we've got to put together an instruction fetch unit. So what is that going to look like? Well, we have instruction memory. Remember, we're going to divide memory into 2 pieces, instruction memory and data memory. We're going to get instructions out of the instruction memory. And of course, these all share an address space. This is just in the hardware. So because we have an instruction cache that we're going to get stuff out of, and we have a data cache that we're going to get stuff out of. So what we need to be able to do is, given a value of the PC, we need to be able to go to the instruction memory, get the 32-bit instruction that's at that location, right, that's defined by the PC, and send that out. So basically, an instruction is 32 bits. When we go to read an instruction, we go to the PC, we find out what address that instruction's at. If it's in the cache, it's going to return right away. If it's not in the cache, there's going to be a little delay. That's going to be a stall. We're going to talk about that later. But let's say it's in the cache, then what's going to come out on this output is the next instruction. Okay, and that's going to be a 32-bit quantity that we're then going to start to decode. And in the meantime, we need some logic for figuring out what's the next address, what's the address of the next instruction. Okay, so at a high level, that's what the instruction fetch unit looks like. Okay, now let's talk about add and subtract. Okay, so now we're really getting serious. So what do we got here? Let's look at this picture first, and then we'll go back up. So here's our register file, right? 32-bit registers, and here are the lines that we talked about. Okay, that's what used to be called the write enable line. Okay, we have an ALU. Okay, and that's basically what we have. We have a clock input here, and and we have our instruction up here. Okay, so what's going to happen? Well, we do the instruction fetch. We get the opcode and the function code. Okay, Opcode says, hey, this thing's going to be an ALU operation. Function code tells us whether it's going to be an add or a subtract. Okay? And then what we do is we start hooking these things up. So RS, what are we going to do? So if it's an add, we're going to take whatever is in register RS. We're going to take whatever is in register RT. We're going to add them together. We're going to take the sum of that, and we're going to write that into register RD. Okay? So how does that work? How does that work here? Well, we have two lines that tell us how to get register values out of the register file. So let's say we're going to put the first register, RS, into this line, RA. So that means the value that's in RS is going to get put on bus A. Okay. We're going to put the value that's in register RT onto bus B. Okay, so now we've got our two inputs. All right, so we're going to take what's in bus A, what's in bus B. We're going to send those to the ALU. They're going to get added together. Result is going to come out, and that's going to be put back into the register file on the bus W, right? That's where the that's where the values that we're going to write into a register go. Okay? In RW, which is identifying which register is going to get written, our destination register is RD, right? So we put RD onto the selector for RW, and we have to do, and now we've got everything wired together. Now, two things have to happen here to make sure everything works, okay? One is we have a control signal into the ALU. It's telling us what operation we're doing. So if it's an add, that has to be set to an add to make the ALU do an add. If it's a subtraction, it has to get the ALU to do a subtraction, okay? And which one of those is going to be, we're going to know that from looking at the function bits. And again, when we start looking at control, we'll see exactly how that control signal gets set. But that's basically the control that tells you which operation the ALU should do. One other thing that has to happen, though, because this operator, let's say it's an add, it's going to write a register. The control logic is also going to have to turn on this bit, right, the write enable bit, which is given this name reg write. So that's the control signal there. So in order for this thing to work, so you see how everything's hooked up. We've got to put the two source registers, RS and RT, onto bus A and bus B, respectively. We've got to tell the ALU what operation it should do, whether it's an add or a subtract. And the result is going to come out of that. We have to make sure that the reg write signal is turned on so that the result of this addition gets put, or subtraction gets put into the register identified by RW, which we've set to be our destination register. Okay, so yeah, there should be some questions here because this is the first time it all comes together. So yeah. Yeah. Yep. Yes. Yeah. So this symbol here says, yeah, there's 32 lines here, and you don't want me to draw them all, not even in PowerPoint. Yeah.
When the write register is on, does that get done before you send it to the
Okay, so it's not going to matter. That's a good question. So when does this signal have to go on, the write register? And the only requirement is it has to be on by when the next clock tick happens, it has to be on. Because that write is only going to happen when the clock raises.
That's not exactly what I meant. I meant if, say, your output register is like register 10, and then your next instruction, it has register 10 as an input,
Yep.
and the write reset happens by then?
Yeah.
Does that mean that you're delayed by your write and the write hasn't happened?
Yes, so that's right. I'll show you a timing chart in a second. But yeah, the write is going to happen when the clock goes up. And if you're reading from that register, which is very likely because you care about it, the delays have to work out. Yeah. Yep. Yeah. This. What do you mean by sequential processor? We haven't done any pipelining yet, right? We will do that shortly, not today. Yeah, so remember, what we're talking about this few lectures is called the single cycle CPU, which is we have these 5 steps of instruction processing that have to happen within a single clock cycle, and we're doing them sequentially. We're not doing any pipelining yet. Once we get this figured out, then we'll figure out how to break that. Yeah? Not exactly. So I made these things red right before class. These two things, ALU control and reg write, are signals that are coming out of controller. We haven't done the controller yet. There's going to be, so there's going to be wires that are actually physically connected to these control inputs. And we're going to build that controller in the next class, not today. Okay? Yeah, good. But we're going to see more and more of these control signals because each operation has its own set of control signals. So let's talk a little bit about clocking, and we'll talk about it more later. But basically, what has to happen here? So remember, this is a single cycle CPU. So here's one clock tick. So the clock goes up, stays up, goes down, and then here's the next clock tick. Okay? So if you want to understand how fast you can make that clock tick, you have to understand a few things. So you have to say, okay, first of all, there's a delay from this register to the time there's an output. Does anyone there's a time from when this clock ticks to the time that this register actually outputs. Does anyone remember what that's called? That's clock to cue, right. Then we have to make it through the combinational logic, right? So whatever the ALU is and any other processing we're doing, there's going to be a path that these signals have to propagate through. Okay? So you have to figure out what's called the critical path, which is the longest path through that circuit, and you have to be able to handle all of that delay. Okay? So you got to figure out the critical path. Then you want to write something to the output, so there's some setup time to make that happen. Okay? And then there's another problem here. Does anyone know? There's a problem that's lurking in a circuit like this with timing. Does anyone see anything else or know of anything else that we have to worry about? It's a little subtle. Yeah. Well, going to memory is a big problem, and we're not even talking about that. But going to memory is much bigger than any problem I'm going to talk about. Anyone else know what's going on here? Think about what this is. Yeah, it's a physical chip. Yeah. I'm sorry, the second and, this one? It will. And that's why you have to let things settle, right? You have to let things, that's why the clock is so important, because that's when you actually write things or look at outputs, right? You have to know when it's safe to look at outputs. What do we call that, the hold? Is that the hold, or is the hold slightly different than that? Anyway, you weren't listening. That's okay. But yes, you do have to worry about that, and you can't look too quickly. Okay? So the other thing that's not up here that can affect things is what's called clock skew. And this is kind of crazy, but even in a small chip, there's differences in how fast current can flow through certain types of gates. There's imperfections in the chip. There's temperature differences. There's a bunch of reasons why electrons are going to flow at slightly different speeds. And so you have to be able to tolerate that as well. Kind of interesting, okay? But that's kind of, now we can start to see what the bounds are in terms of how fast we can make that clock tick. And it's this summary of the various delays plus just the amount of work you have to do on this critical path, plus a few of these side things like clock skew and stuff like that. Okay? But once you've got that timing figured out, here's another way to look at it. This one's a little bit of an eye chart, and I'm going to have to read through it with you. So, but, we're going to look, so what we're looking at here is one complete clock cycle. Okay, so here's the clock going up, and then here's the next clock tick. So between these two dotted lines is one cycle. And remember, we've got to do our fetch, instruction fetch, decode, we've got to do the ALU, we've got to get stuff from memory. If we can't get it right away, we're going to stall. Right, so if it's not in our level 1 cache, we're going to stall. And then we have to do a write to the register if we need to. Okay, and all that has to happen between these two dotted lines. okay? So if you start reading down from the top, the first thing we need to do is we need to read the PC, okay? So there's going to be a delay, the clock to cue delay of that PC register. And so at this point, so the clock's gone up. At this point, we now see the new PC value, okay? And so we continue. The next thing we do, given that we've gotten that address, right, the PC tells us what address the next instruction's at. Given that, we have to go to memory to get that instruction. And even if it's in the cache, that's going to take a little bit of time. It's got to be less than a clock tick, right? Remember, our level 1 has to be fast enough so that we can get this done in a clock tick. But there's going to be some delay from the time we know what the address of the instruction we want to the time that we actually get the instruction. So that's called the instruction memory access time. Okay, so at this point, we now know what instruction we're running. Okay, that's good. So then we keep going. Once we have the new instruction, let's say it's an add or a subtract, because that's what we're talking about now, we've got to do two things in parallel. Okay, the first thing is we've got to decode the opcode and the function code, right? Because we've got to know, what is this thing? Is it an add? Is it a subtract? Is it some other operation? So we've got to do that decoding, and then based on that decoding, we've got to set the ALU control and the register write control signals accordingly, okay? So that's got to happen. So that's called the delay through the control logic, okay? That's one thing that's happening. The other thing that's happening, though, is remember, we've got to be reading the registers, okay? So when we decoded that instruction, we saw that, let's say it was an AND, we know that there's two registers that we're going to have to get out of the register file and send to the ALU. So that's what's happening over here. We set, at this point, we've got ALU control set to its new value, and register write is set to its new value, right? So once we've gotten through the control logic. At the same time, we're going to the register file, and we're getting the registers we need put on bus A and bus B. So that's the register file access time. Okay, so notice that those two are happening in parallel, going through the control logic and setting the control flags, as well as getting the values out of the register and putting them on bus A and bus B. Okay, once we have the values that we want on bus A and bus B, remember those are the input into the ALU. So now there's a delay to actually do the operation. Is it an addition? Is it a subtraction? We know it's going to do the right one because back at this point, we set the ALU control bit to be the right value. So the ALU is going to do its stuff. At that point, we've got a new value. We go back and we put that on bus W. And then remember, the write is only going to happen from bus W, right? We go all the way around back into the register file. The write happens because we have the register write flag set. The write happens right there, right at the beginning of the next clock tick. Okay, and then we start again. So that, on a single slide, is basically showing you, the entire process of that five-step instruction execution process for an arithmetic operation. Quick question, and then we got to run. Is the register file access time longer than the delay through the control logic? I'm not sure it's drawn this way here. I'm not sure this is to scale. Yeah, okay. All right. So, all right, but no clicker.